So now we're going to discuss the units of measurement. Because chemistry is an experimental science, so all the stuff that's in your book is actually based on experiments that people did hundreds of years ago, you actually have to look at measurements because, and even in your word problems, all those numbers are supposed to be based on some sort of experimental measurement that somebody did. So two common units of measurement are the metric system and the English system. The metric system is what gets used in the rest of the world. The English system is what's used in the US. Scientists use International System of Units, the SI system. So the System International, these are mostly metric units. So here are the standard SI units. So for length, we have meter, and there's a symbol for meter. For mass, we have kilogram, and there's a symbol for kilogram. Time, seconds, there's a symbol for second. Temperature, Kelvin, and there's a symbol for Kelvin. Amount of substance, the mole, and there's the abbreviation for mole. Electric current, ampere, there's the abbreviation for ampere. Luminous intensity, candela, and there's the symbol for candela. When we're using International System of Units, we use prefix multipliers, and they're in the next table that I'm going to show you in a minute. And the reason why you want to use these multipliers is because you just multiply everything by 10. When you're doing English systems, you have things that you have to memorize like 12 and 3 and 4 cups in a, 4 cups in a quart and things like that. So here, everything is just based on 10. So all you have to do is memorize a part of that table that I'll show you in the next slide. So here are my prefix multipliers. Now, there are a lot of prefix multipliers. You don't have to know all of them. You only have to know just a few. So the ones that I want you to see are, here is the kilo. So you have to memorize this. So I want you to memorize the one with the red arrows. So here's kilo, here's centi, here's milli. And that's really pretty much all you really have to memorize. So kilo is 1,000. So this is a very large unit. Centi is a very small unit. It's 100th. And milli is even smaller than that. It's 1,000th. So you can also look at this in terms of scientific notation. So 1,000ths would be 10 to the minus third. We can also look at the difference between intensive and extensive properties. So intensive properties are properties that are independent of the amount of substance. So density is an intensive property. So an extensive property is something that is dependent on the amount of stuff you have. So mass is extensive, volume is extensive. So why is density an intensive property? Because density is equal to mass over volume. So density it doesn't matter how much you have, density is always the same, no matter how much of it you've got, because you're actually dividing an extensive property mass by another extensive property volume. Counting significant figures. And because, as I said, because chemistry is an experimental science, you have to sort of look at significant figures. I cringe when I see people writing out answers to questions, word problems, and they just write down every number that they have and that their calculator spat out at them. But you really shouldn't be doing that because chemistry is an experimental science. The number of significant figures depends on your measuring device, and it depends on the instrument that you use to do the measurement. So you should only give enough significant figures for the instrument that you use to make the measurement. And when you're looking at significant figures, you're actually embedding in your calculations and in the numbers that you're writing down how good your measuring device was when you were doing the experimental measurement. So when you have a larger number of significant figures, the more certain the measurement. So if you have numbers that have lots of significant figures, that means your instrument is really, really good. So here's what we use to determine significant figures and numbers that are written out. So here are my significant figure rules. So first, all non-zero digits are significant. You shouldn't write down if it's an experimentally determined number and you do some sort of math, you shouldn't write down numbers that are not significant. But when you see a number written out like this, all of the numbers in pink are significant because they are non-zero. Interior zeros are zeros between two non-zero digits are always significant. So here, my 0 here and my zeros here, these are also significant because they are inside of non-zero numbers. So we want to look at, there's some examples there, and then we're going to look at the rules. So leading zeros, zeros to the left of the first non-zero digit are not significant. So these, not significant, because you're basically using these numbers just to be able to tell that this is actually a thousands and not 32. It's not really anything other than a placeholder. So leading zeros are not significant. Trailing zeros, there are rules about trailing zeros. So if you have a trailing zero after a decimal point, so there's my decimal point, and there I have a bunch of trailing zeros. So these are significant because the zeros come after the decimal point. So these pink zeros here are both significant. Trailing zeros before a decimal point are always significant. So here's my decimal point. So this is a significant figure because it is before a decimal point. Here's my decimal point. So these zeros are significant. So if you have a trailing zero and you didn't actually implicitly write out the decimal point, so see here, I don't see any dots here. There is no point after the 1200. So there is no decimal point. So that is ambiguous. Meaning you would have to have these zeros in order for it to be 1200 as opposed to 12. So you had to put them in because they are placeholder zeros. But it's possible that you actually measured something down to the last one. So you actually measured 1200, and it wasn't 1201, it wasn't 1199, it was actually there. So it could be a significant figure. So what you do to avoid confusion is you use scientific notation. So here we have two significant figures because you didn't write down any of the zeros after that. Here we have three significant figures because this number here, this 0, is a 0 after the decimal point, so it is significant. Here we have zeros after the decimal point, so it is significant. Here we have four significant figures because you wrote down the decimal point. So when you're dealing with zeros, where you put the decimal point sort of determines whether the 0 is a significant figure or not. So you have to be very careful about that. And you want to try to avoid this ambiguous situation because you can't tell how many significant figures you have in that case. Okay, so continuing on significant figures, exact numbers have an unlimited number of significant figures, an infinite number of significant figures. So when you have an exact number, you get an exact counting of discrete objects. So if you have like 12 eggs and they're 12, it's not like 12 and a half of a broken egg, it's just 12. So these are discrete objects, so that's exact counting, so it has an infinite number of significant figures. If you have integral numbers that are part of an equation, then that has an infinite number of significant figures. If you have a defined quantity, like you know that there are 100 centimeters in a meter, and that is defined, there are an unlimited number or an infinite number of significant figures in that number 100 centimeters per meter. Some conversion factors are defined quantities, others are not, so you have to keep in mind which are defined and which are not. Significant figure rule for calculations. So when you do multiplication and division, you have this rule. In multiplication and division, the results carries the same number of significant figure as the number with the fewest significant figures. So what you have to do is you have to count the number of significant figures for all the numbers in your multiplication and division, and then you use the least number of significant figures for the final answer. So here are some examples. So here we have 4 significant figures. Here we have 5 significant figures. 1, 2, 3, 4, 5 significant figures. Here we have 2 significant figures. That leading 0 is not significant, so there are only 2 significant figures here. This is what your calculator spat out. So it looks as if it's got 1, 2, 3, 4, 5 significant figures. But that's not what the educated person is going to write down for their final answer, because they're going to look at the number and you're going to say, 2 significant figures. This is the least number of significant figures. My answer can only have 2 significant figures, so I end up with 6.7 for my final answer. Here I've got 5 significant figures. 1, 2, 3, 4, 5. Internal zeros are always significant. Zeros after the decimal point are significant, so there are 3 significant figures here. This is what your calculator spat out. It looks as if you got 1, 2, 3, 4, 5, 6 significant figures. But we know we can only have 3 significant figures because this is the least number of significant figures. So we have to round it down to 3 significant figures.